Great. So we're very happy to have Florent Baume here to tell us about the distance conjecture holographically. Well,
okay, so let me join everyone and thank John and Cody for this great seminar series and giving me the chance to talk about the paper that came late last year with Jose Calderon at the IFT in Madrid. So this is a Swampland talk, so let me start with my mandatory Swampland slide. So we want to learn about quantum gravity by studying the constraint it imposes on effective field theories. And this has, in recent years, led to a revival of the Swampland program, which is based on a set of various conjectures. And today I will talk about the Swampland Distance Conjecture, which says that, so I can set the tone and the notation, that if you move in the moduli space, which is the space parameterized by massless fields, then as you approach a point is at infinite distance from a reference point, then you will get that there is an infinite number of fields that becomes massless, and they become massless exponentially fast with the distance in the moduli space. So there has been lots of work on this, but most of it was in flat space, and comparatively there have been less done in AdS spaces. So this is what I'll focus on today. And I'll just note that in the usual flux compactification approach, for instance, then some of your moduli might acquire mass, might get stabilized, for instance, by fluxes. But when I say moduli space, I will only mean states that stay massless after taking everything into account. So generically, my AdS moduli space will be smaller than the one in flat space. And then from there, you have two kind of directions you can study. Either you can move the AdS radius, but in AdS compactification, the AdS scale will usually be related to the volume of the compact manifold. This direction that was studied by Lust-Paltier and Waffa 2 years ago. And they came up with the AdS distance conjecture, which says that as you vary the AdS scale, so the radius, you have a KK scale, a KK tower that becomes massless at infinite distance. This is not really what we want to do. We want to keep the AdS scale fixed throughout the trajectory, and then ask the question, what kind of tower can we, if any, can we have? So the way we want to do that is through the AdS CFT correspondence, because there is a huge machinery that has been developed through the years. And I'll focus today only on 5 dimensions. The AdS CFT correspondence tells us that for any fields in 5 dimensions, then on the boundary, I can associate an operator for a conformal field theory. So the data in AdS can be transferred to the data of the CFT. And for instance, the mass of the fields for any field will be associated to the conformal dimension of an operator, of the associated operator in 4D. Now, this is not the first time the holography has been used with the Swampland. There have been work on global symmetries with gravity conjecture and also some positivity constraints. And there are actually been talks in this seminar series. But comparatively, nothing has been done for the SDC, except, and I mentioned it here, a very nice paper that came out about the same time as us by Perlmutter, Castelli, Waffa, and Valenzuela, who study similar IDs as we do. So this is a very nice complementary paper. So all these studies basically boils down to the fact that unitarity is very constraining for conformal field theories. And in our case, we'll use the fact that if you have conformal symmetry, you have additional generator, like the dilatation operator. And the charge of the dilatation operator is the conformal dimension, just as a quick reminder. But through unitarity, you can see that it's bounded from below. The bound depends on the spin. So for scalar, it's always greater than 1. And then for higher spin, the bound depends on the spin. And here, I'll quickly note that I'll be very cavalier when I say spin. I always mean traceless representation, traceless symmetric representation of the Lorentz group, so integer spin. And these bounds are saturated by either free fields or currents. So if I have in the case of the scalar, the dimension is saturated at 1, and this is the engineering dimension of a free field. And if I get an interacting theory, then the anomalous dimension will get corrections. But there are other fields, other conserved currents that have a fixed dimension. So for spin 1, I have the flavor current, spin 2, the energy momentum tensor. And if I go to higher spin, then I have the so-called aptly named higher spin currents, which generically take this form. You sandwich a bunch of derivatives between two scalar fields. And the reason these guys are interesting is that there is a nice theorem by Maldacena and Shiboedov from about 10 years ago, who says that if you have one of them in your theory, then your theory is free, or at least there is a sector of your theory that completely decouples. And moreover, if there is only one of them, if you find one of them, then you are ensured that there is an infinite number of these higher spin currents. And while we're in the Swampland context, if I have an infinite tower of something, then this screams Swampland Distance Conjecture. So this is what I'll explain now. How can we relate these currents to infinite distance point? So before I do that, let me just say that in the Swampland Distance Conjecture, we are in AdS space. So how can I translate distances in the moduli space into something that has to do with the conformal data? Well, the way you do that is that you take your dictionary between the mass and the conformal dimension. And as I said, the moduli are scalar fields that are massless. And if you plug that here, you will find that this corresponds to marginal operators. So instead of having a moduli space, I will have what's called the conformal manifold, which parameterizes how you can deform a CFT without breaking conformal invariance. So if I have a Lagrangian description, I can just perturb it with an operator. And if this coupling constant has vanishing beta function, then it's a coordinate of my conformal manifold. And it's a manifold, so it has a metric. And you can, at least in principle, compute it by looking at two-point function of the marginal operators. Now, so just to summarize what I said so far, instead of talking about the moduli space and trajectories in it, I can instead talk about distances inside the conformal manifold. The metrics will be just related by a change of unit factor. And always keeping in the back of my mind that if I get a higher spin conserved current, then my theory is free, or at least the sector is free. Now, the best way to demonstrate how this is useful is to just take an example, and the simplest example you can think of, it's the celebrated AdS5 cross S5 in type 2b with n unit of 5 flux. And if you go through your favorite textbook, you'll find that the AdS radius is indeed, as I said before, related to the radius of the phi sphere. And in the AdS scale in Planck units will be fixed by the flux number. So here I will not take something that varies. I will always pick it constant. Pick your favorite number, and you can leave it at that. So that fixes one of the moduli, and the only one left is the axial dilaton. And this is something we know and love in the Swampland. So we know that the associated metric is just the hyperbolic metric, and that's the distance is just the logarithm of the imaginary part. And then you have a one-dimensional moduli space, and it has two infinite distance points at 0 and I infinity, so which are just related by duality. So that's in the AdS part. If I go to the CFT now, I get n equals 4 super Young mills with gauge group SUN. And here everything is fairly simple. I only have the vector multiplets with a scalar fermion and a gauge field. But you have to remember that CFTs only care about a gauge invariant operator. So instead of talking about this, the operator I want to consider are, for instance, the trace operator. And moreover, the only parameter in your theory, well, you have two real parameters, the Young-Mills coupling and theta angle that you combine into a complex variable. And it turns out that in that case, this is just the axiodilaton. So okay, we have two different sides of the coin. Oops, sorry. And of course, as I said, you have a metric on this moduli space, and you can go through the computation, and you'll find that the sum logic of metric, the metric of the conformal manifold, is just the same as the metric of the moduli space. Now, why is it useful? Well, it's useful because the infinite distance point is at small coupling. So I can, instead of having something where GS is very small in AdS, I can just use perturbation theory in the CFT. The quantity of interest is the conformal dimension, so it's just a small perturbation away from the free field value. But at the same time, I also know what the metric looks like, so I can convert my Young-Mill coupling, and instead of having the distance. And here, I find that the conformal dimension would just be the free value plus a small perturbation that decreases exponentially fast with the distance, which is exactly what we want in the context of the Swampland distance conjecture. Now, this is on the conformal side. If I want to go back to the gravity side, well, I know that I have this from Maldacena-Zhiboredov, that I have these higher spin operators, which away from the free point will not be conserved, but I know that they saturate the unitarity bound at the free point. So I can just plug back in my formula for the mass, and I will find that I have higher spin fields that become massless exponentially fast with the distance, which is exactly what the Swampland distance conjecture is telling us. So just to summarize, I find that I have a tower of higher spin fields that have the exact property we want. But something that's very different from flat space is that I do not have a scalar, a tower that becomes massless. If you do the same thing for scalars, you'll find the mass will be some integer constant plus the exponential here. So this is a striking difference between flat space. In flat space, we always have scalar, and in AdS, it turns out that we don't. So you can ask, well, what's the origin of this tower of states? Well, in AdS 5 cross S5, it's pretty obvious. The Young-Mill coupling is just GS, so we get the tensionless F1 at the infinite distance point. And moreover, you can look at what you get for the decay constant, and it's just the central charge of n equals 4 divided by the dimension of the gauge group. And if you plug the formulas, you just find another one number, which is exactly what the Swampland distance conjecture is telling you. So all in all, at least in that case, the Swampland distance conjecture is just a consequence of the Maldacena-Zhiboredov theorem, which tells you that at free points you have this infinite tower of conserved currents. Now, this is n equals 4. It's the the most constrained conformal field theory in 4D. So you can say, okay, this is just an accident. But so we can go to the next simplest case, which is n equals 2. And there, the marginal operator you were interested in are marginal, of course, dimension 4. But you also want them to preserve n equals 2. And if you go through the full list of the type of multiplets you can have, you will find there is only one candidate for the marginal operators, and they are inside the so-called E2 multiplets. That's a member of the chiral ring, if you're familiar with the Delano-Spohr notation. If you're not, it's not a problem. Just if you have a Lagrangian description, then the marginal operator is just a change in the gauge coupling. So at least morally, n equals 2 is basically the same as n equals 4. You just have a richer network of infinite distance points. Instead of having one gauge group, you can have a bunch of them. And instead of having a one-dimensional conformal manifold, you can have the dimension you want. And of course, you can again play the same game and do perturbation theory. But generically, if you decouple one of these gauge group, it doesn't mean that the operator will have vanishing anomalous dimension. However, you know, again from Maldacena-Giboedov, that in the vector multiplet sector, you will have a scalar inside the vector multiplets. So you can construct a higher spin current, a higher spin operator like this, and you are assured that at the free point, this guy becomes conserved. So then the question is, do you also have an exponentially something that decreases exponentially with the distance? And it turns out that in n equals 2, you can, around the free point, you always find that the Zamolodchikov metric, the metric of the conformal manifold, is just the usual hyperbolic metric we know and love plus subleading corrections. So I can play the same game, transform the coupling into the distance, and I find that the anomalous dimension has exactly what I want. So if I go back to AdS again, I will find higher spin fields that become massless. So this is exactly the same as in n equals 4, and it's something that's fairly generic. Okay, but this is I only discussed 3 points. So you can ask, okay, we know that if I get a 3 point, I have an infinite a tower of higher spin fields, and I'm at infinite distance. Can I prove the reverse? Well, we do not have a general argument, but you can at least look at the relevant candidates. So the first thing you can say, okay, can I have a singularity in my conformal manifold where I have a flavor enhancement, for instance? Well, if you have this, then that means that you get a new flavor current. But if you look at the representation theory in n equals 2, you will see that this new flavor current is always accompanied by a higher spin current, which means by Maldacena-Giboedov that those are just 3 points. So I can only have flavor enhancement at infinite distance. You can, using the flat space lore, let's say, can I have a tower of scalars? Well, if you get a tower of scalar in the bulk, that would mean that you get an infinite number of marginal operator in the CFT, which means that the gauge group will have a rank enhancement that's infinite. And at least to my knowledge, there are no known examples for these. So this also seems excluded. The last thing you could say, and this is maybe the most natural thing, is that instead of going to weak coupling, can I go to very strong coupling? Well, in this case, at least from the classes construction of n equals 2 theories, I know that if I go to infinite coupling, I usually have an S-dual frame with maybe a different gauge group, where instead of being at infinite coupling, I get something free. So in the appropriate frame, this will always be a free point. So just to give an example of such cases, you can take AdS5 cross S5 mod ZK. And this is also something that's very well known in the AdS CFT community. And you will have an orbifold singularity that you can blow up, and you can integrate the two forms over the blow-up cycles, and you will get moduli that maps to gauge coupling of a gauge group SUN to the K, n the flux number, and K the order of the discrete group. And then a natural direction you can go is to say, okay, can I just take these two axioms to 0 and go to strong coupling? Well, at least in that case, you know exactly what happens. You know that there is an S-dual frame where there is an SUK that decouples. So this is one of these examples where you would a priori say, okay, this is infinite distance, but not free, but in the appropriate frame, it is indeed free. And something that's very interesting, at least to me, is that contrary to in flat space, axioms are usually related to compact direction of the moduli space. But here, the infinite distance points is driven by axioms. So it's kind of a novelty of AdS. Now, this is just one example, but you can generalize it to a bunch of classes theories that have a weakly coupled dual in M theory. And there has been studies to know where you can have a decoupling limit. And if you have the classes data, then you can say yes or no, I have a free point. Okay, so I guess I'm close to be out of time. So I'll just finish by saying that if we want to prove that infinite distance is always free, then there is a related conjecture in the n equals 2 literature, which was proposed in this paper here, which says that if I take any CFT with a conformal manifold, then it's conjecture that I can just obtain it from gluing together a bunch of theory without a conformal manifold, just by gauging flavor groups. And it seems that to indicate that since the only thing I can do is gauge flavor groups, and I know that free points are at infinite distance, free point being when I decouple, when I ungauge, then there seems to be a relation. So it would be very interesting to see from that point of view if we can prove both sides. So let me summarize and conclude. So we studied the Swampland Distance Conjecture in AdS, and we find that infinite distance points are associated to tower of massless higher spin fields instead of scalar fields at those infinite distance points. And what happens there, it happened in the example we checked, but we conjecture it always happens, is that in the CFT dual, there is a sector that decouples. So this was for n equals 2. So we think this happens in any SUSY, but one can check what happens. And this was actually done in our, call it our cousin paper. They looked at 4D n equals 1. So in 4D n equals 1, you can also have superpotential deformation that stay marginal. And in those cases, they found that these guys were compact directions, and the only infinite directions were still decoupling some gauge sector. And something also we would like to do is to see if we can have a geometric proof, either in AdS or in CFT in n equals 2. And we have, in flat space, we have all this nice technology from variation of Hodge structures. So it would be very interesting to see if we can use similar arguments to classify all the infinite distance points. And I'll conclude by saying that CFT arguments start bleeding into the swampland. So it's a great opportunity to see if the Bootstrap program and the swampland program can learn from each other by taking arguments. So let me thank you for your attention.
Great. Let us all thank Florent for his very clear talk. I guess Ben has a question/comment.
Hi, thanks very much for the talk. Very nice. I'm not totally sure I understood something, and so I wanted to ask about it and also make a comment. So I think you said that in the n=2 case, if you had an enhanced flavor symmetry, then it would be a free theory at that point?
Yeah.
Right,
Yeah.
so my comment was that that's not true in the n=1 case.
Yeah,
but I'm not sure what it has to do
sure.
with what you're saying.
Sure. So the new flavor is free. It's just you can see it by looking at the superconformal representation. But
Sure.
that's very true that this is really n=2. If you go to n=1, I guess it happens sometimes, not always. I'm not sure.
So for example, if you take SQCD with NF is 2NC, then there's some SU 2NC times 2NC flavor symmetry that gets broken as you move out along a conformal manifold.
Okay.
But the point you start from is interacting.
Yeah.
But so what does that mean? I guess that maybe that points at finite distance.
So
is the point, yeah.
So that's what. So I don't know that example very well. So, but I would expect that this is either at finite. Well, no, this is at finite distance, yes, since it's not free.
So it's at finite distance, but you can have a that's interesting from a Swampland perspective, right? Because you have an enhanced symmetry. Well, I guess yeah, I guess that doesn't mean that the
the new flavor symmetry will be in the CFT. That doesn't mean in the AdS that would point to a gauge enhancement, I guess.
Yes, but then I guess maybe it's Higgs or something. I'm not sure. Okay, I was just wondering if there was a Swampland interpretation for what's going on there versus what you said in the n=2 case. That was my question. But sorry for being slightly vague.
So I don't know about that particular case. And at that point, we only studied the n=2.
Okay, thanks.
Okay. So Irena has a comment in the chat, but it seems like there are no more questions. So let us end this session and thank both Florent and Severin again for their very nice and very clear talks.